This is section 3.2, the derivative as a new function. And in this section, we will try to focus on the graphs of the derivative and the relation of the graph of the derivative to the original function. Let's start with the definition. A function f is called differentiable if the derivative it's differentiable at a, at the point a, if the derivative at a exists, if f prime at a exists. Now, the function f is differentiable on the open interval, and we may have an interval from a to b, from negative infinity to positive infinity, and basically we can have any interval, and function will be differentiable there if it is differentiable at every single number in that interval. Okay, so this is the definition. Now, let's start with this exercise. I believe we did similar exercise, but let's find the derivative of the absolute value of x. First of all, we can state the domain. Domain of absolute value of x is all of the real numbers. We also know the graph of absolute value of x based on the definition, absolute value of x. If x is positive, then we can ignore absolute value is just x, y equals to x, but only for the positive part, y equals to x. If x is negative, less than 0, then that quantity is negative, we have to make it positive. And negative x, y equals to negative x is this graph, but only for the negative part of the x-axis, negative x. And this is the graph. And of course, if x is 0, absolute value of 0 is 0. Okay, but what I will do, I will actually remove that 0 for a second. 0 is still in the domain. It's not a problem, but we do have a problem. We know that with respect to the derivative. And now we don't even have to compute the derivative using the limit. We will do this at 0. Derivative of absolute value of x, actually, I will skip this. We know what derivative means, is the slope of the line, slope of the curve. Slope of function y equals to x is 1, y equals to negative x is negative 1. Okay, that's derivative, and I can even say derivative is 1, and derivative on this side, y prime is negative 1, for the positive x and for the negative x. Okay, excellent. However, we do have to perform one task. We have to find out what is the derivative exactly at 0. At 0. We will use the limit definition because that's the only tool that we have. Limit as h approaches 0, f of a plus h minus f of a all over h. Limit as h goes to 0. A is 0, 0 plus h, f of 0, and h. Maybe I can squeeze it here. Limit as h goes to 0. Absolute value of 0 plus h, it will be just absolute value of h. The absolute value of 0 is just 0. We don't even have to write this down. And all over h. I can even remove this. Okay. Now we have a situation that we have to check the 0, but that's different. The h quantity is approaching 0 from the left and from the right-hand side. Okay, I can say limit as h goes to 0 from the right-hand side, then h is positive. We may ignore absolute value, limit is 1. But now when we will try to compute a limit, as h is going to 0 from the left-hand side, it will be negative h over h, negative 1. 1 and negative 1. Two different one-sided limit. Limit at 0 does not exist. Okay, So we have the proof based on the definition, and we, of course, remember we did the general statement. If function has this shape like a sharp corner, sharp turn, we will be not able to draw a tangent line, because tangent line and the curve, they're supposed to have the same direction, like they have to be almost indistinguishable at that point. And when we will try to draw a tangent, we don't, that's not right, of course, that's not good, okay? We do not have a tangent, no at 0, at that sharp corner, no tangent, no slope, no derivative. Okay, and now let's actually try to get the graph. Y prime equals to 1 constant function. Oh, actually this is y and this is 1. For all of the x's greater than 0. For all of the x's less than 0, value of the derivative, this is derivative, if I can say this way, is -1. Okay, and at 0, we have empty, like no value. This function is not defined as derivative. Derivative does not exist at 0. Let's find out what is going on with this function, x to the power of 1/3, or if we prefer, we can say cube root of x, but the power form will be good. Okay, for this one, I will take the advantage of the formula, the power rule. Derivative with respect to x of the function x to the power of n is equal to nx to the power of n minus 1. 1 less than it was the original. Okay, derivative of the function x to the power of 1/3 equals to 1/3 x to the power of 1/3 minus 1. 1/3 x to the power of -2/3. And we're supposed to provide the final answer without the negative exponent. X to the power of -2/3. Negative is telling me that we have to go to the denominator, like the flip, we have to flip the number instead of x1 over x. And power 2/3 is telling me that I will take cube root and squared. Okay, this looks like a good form of the derivative. And this is derivative. I can say actually not f, g. This is g prime of x, just different notation, g prime of x. And now algebraically, looking at this formula, looking at this fraction, we can see 0 in the denominator. Domain of this derivative, I can maybe indicate, are all of the real numbers except 0. Or speaking really basic notation, 0 is not in the domain. At 0, this expression is not defined. At 0, this derivative is undefined. I can say g at 0 does not exist because 0 is not in the domain. So this is one of the way to also check if function is differentiable at the certain point. We certainly can draw a graph. X to the power of 1/3 looks like this. We know it's the inverse. It's the inverse function to the x cube. And we remember we do have a vertical tangent at 0. Yeah, that's actually graphical explanation. We have vertical tangent. Okay, at x equals to 0. Vertical tangent has no slope, no derivative. Okay. Okay, we have this geometrical statement, we may also try to draw a derivative. Okay, let's actually check. One thing, and I can indicate this, one thing that we may look at this expression one more time, we have x squared, and all of the quantities are positive. We can also say that the derivative is always positive. If it's always positive, we know that the function will be actually, derivative, the other way. If the derivative is always positive, we may notice that the slope of the tangent lines, except zero, of course, except zero, slope of the tangent line is always positive. Yes, slope of tangent. It's also greater than zero, and we can see positive slope, positive slope, positive slope, positive, positive on the entire like interval of the domain, from negative infinity to positive infinity, excluding zero. Okay, so we have this, and also another conclusion is knowing that derivative is positive, function actually is increasing, because if the slope of the tangent is positive, we can say function is increasing. But we do have some conclusion. Okay, we still need a graph. Let's try. What we see, definitely the graph of the derivative is not defined at zero, no value at zero. Now, values of the slope will give us the values of the derivative. And what we can say that this slope is almost horizontal, small, not zero, but small. Like this slope will be small. This one will be a little bit more. We can see this line is a little bit steeper. This is a little bit more steep, then the value is bigger. And we're approaching this green point, which is actually vertical line. Yeah? But before that, we have huge slopes. That means all of my blue dots, if I will connect them, they represent the value of the slope of the tangent lines for the original graph. Okay, that's the graph. Now we are on the positive part. This slope is like, let's say, huge, and it's getting smaller and smaller. It means from the huge values, we're approaching almost zero. Okay, the blue graph is the graph of the derivative. And we do have the formula. That's the formula. Okay, now I have just like I combine everything, because we did say a little bit in the previous video, in the previous session, how can a function fail to be differentiable? Of course, we know the corners. That's not a question. We know the vertical tangents. We just did it. And of course, we also learned that if function is discontinuous, if we have discontinuity, we may also think, how can we draw a tangent line at this endpoints, or even if we do not have a point, even if we have a point defined, we will never be able to draw a tangent line. That's the reason that if function is discontinuous, we can also say no derivative. Function is not differentiable at this point. Okay? So we have these three possibilities. Okay? Corner, discontinuity, and the vertical tangent. No derivatives. Derivative at A, D and E. Derivative at A, D and E. And of course, derivative at A, D and E. Perfect. Okay, now we have important theorem, okay? And this one, if function f is differentiable at A, then f is always continuous. Yeah, because now we will try to connect continuity and differentiability. If it is differentiable, if the derivative exists, Yeah? I can say if f prime at A exists, yes, then function is continuous, and actually I can say the definition of continuity. If A, of course, is in the domain, and if the derivative exists, then limit of the function as x is approaching A, it's the same like the value. That's actually the definition of the continuity. I just stated this theorem using the mathematical symbols. If derivative exists, function is differentiable, that's the meaning. Then function is always continuous at A, okay? Also, we can say if f is not continuous at A, then it's not differentiable. That's just a different way of saying this. However, we have to be careful. Converse of this theorem, okay, is actually false. And what this means, we can simply interchange. I can say if function is continuous, then it's differentiable. And that's not true, because we can draw a function, and especially this is our good example. Absolute value of x is continuous function, but we know it's continuous at 0. However, we know that derivative at 0 does not exist because we do have a corner. Okay? So if we have continuity, we may not have derivative. However, if function has the derivative at a certain point, always will be continuous at that point. And I have a couple of true and false questions. You may pause the video and you may try to answer the question before we answer together. Then you will check if you will understand. Okay, question 1. If f is continuous at A, then it's differentiable at A. Of course, is false. And I just say, maybe I can say this is absolute value of x is a great example, or a little bit too thin. Because absolute value of x is continuous function, continuous at 0, but it's not differentiable. I'm sorry, I just hit something on, but f prime at 0 does not exist. Okay, that means this is definitely false. Okay, statement number 2. If f is differentiable at A, then f is continuous at A. Of course, we know that this is true because that's actually our theorem. Okay, statement number 3. If the limit of the function f of x as x is approaching A exists, then f is differentiable at A. Okay, let's actually try to draw something. Function f of x, let's pretend that this is the situation. Okay, limit exists. Yeah, I just put L. Limit of the function f of x as x is approaching A. We can see function is approaching that open dot, is approaching that open dot is at the level L. Yeah, exists. However, we do not have the value. Function has discontinuity, removable discontinuity. Then it's not differentiable. That's also false. Okay. Now, statement number 4. If the derivative exists, then the limit is the same like the value at the point A. You may notice, I can give you a couple of seconds to answer before me. Yes, I hope you answer correctly. If f is differentiable at A, this is the same Actually, x, yeah, I could put a, but x from the domain. Actually, no, I will prefer a. Then that's the same thing. And then f is continuous at a. This is the definition. Right? That means I just use the same statement number 2 and statement number 4 are identical. Just using different wording, I can say, and this is of course true. If the derivative exists, function is differentiable at a, then limit is the same like the value. Of course, function is continuous. That's the definition. Okay. Okay, let's do the next example. We have a function and we have to find out all of the values of x, just the x coordinate, where the function is not differentiable. Let's label properly. Okay, probably the first one will be -2 because we do have a corner. Probably the next one, you will tell me -1 because we have vertical asymptote, we do have discontinuity. Also, we can say 1, another discontinuity. Also, we can say 2, removable discontinuity, and of course 3. And we assume that function goes like, let's say, up, and function goes to the infinity. Okay, that's how we can identify corners, discontinuity, and vertical asymptotes. We do not have vertical asymptote here. I'm just assuming that we do not have it. Okay. Okay, now we will try to match. Okay, the green or blue, turquoise. The green graphs are the graphs of the function, and the pink one, that the graphs of the derivatives. And let's try to match them. How can we find out? Okay, let's look at maybe graph B. Graph B, because it's straight, it's just the straight lines. Okay? This, I'm assuming, because what we can do actually now, we can use this property that the derivative is the slope of the tangent. That's helpful. Slope of tangent. Okay, I will say this slope is definitely positive, and slope, of course, represents the derivative. Let's say 1. Yeah, the same will be that slope, which is derivative 1. This slope is, let's say, -1. And we can nicely see 1, the horizontal line 1, 1, and -1. Right? And of course, at the corners, we have no derivatives here, no derivative here. I can also say -1 and 1, but that's the x values. Okay, that we can see. B corresponds to 4. Okay, I can use B and 4 the pair. Okay, now, we can look at the graph A. Graph A it's not a straight line. Then we have to be careful because the slope is changing. But first of all, I will draw horizontal tangent. Slope is 0. Slope is 0. Value of the derivative supposed to be 0 here and here. What we have? We have here 0 and 0. Let's say -1 and 1. -1 and 1, only 2 zeros. And now, if we will draw the slope here, really big, steep negative numbers. I mean, big negative sounds funny because big negative is actually small number arithmetically, but I'm just saying steep, which will be magnitude, the absolute value of this number will be huge, but negative, and it's actually approaching 0 and makes sense. Huge negative, and it's approaching 0. And then starting from 0, the slopes are positive, 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 but starting from 0 is approaching 0. It means positive, like steeper, and then again, less steep. Steep, yeah, attaining some maximum value, which probably is at 0. Actually, it is. And again, getting back to 0. And then all of these slopes slope still like symmetrically, big positive now, big negative numbers, big negative numbers. We will go to negative infinity. Definitely A matching the second graph. Okay, maybe D, because I nicely see horizontal, horizontal, horizontal. Slope is 0, slope is 0, slope is 0. We need 3 zeros, 1, 2, and 3. Big numbers, slope huge, slope huge, huge. Then we can see huge numbers, but approaching horizontal, approaching 0. And then negative numbers, approaching 0, and positive numbers and approaching 0. And again, huge negative numbers. Negatives will go here. D, match 3. And now I hope we have no option. C is matching the first one. Let's double check. Horizontal tangent means slope is 0. Derivative is 0. We have zeros. And then now these slopes are negative, but small negative, because almost horizontal lines. And it's approaching 0. That's we can see small and then approaching 0, because at some point the slope is quite, bigger. I'm saying the line is steeper. The magnitude is bigger than this one, as we have to go lower. And symmetrically, we have the same on the other side. It's a little bit bigger, a little bit. Now it's less steep, and almost horizontal. It's attaining some maximum slope, right? We can see at some point is the steepest, somewhere here. That will be the value, steepest, and then it's almost 0, almost 0. Okay. Playing with the slope of the curve, slope of the tangent, we can easily try to plot these values and connect them to getting the graph of the derivative. Okay. Let's solve this question. This one is not really relating to the graph, but it's a nice question. Let's solve it. Consider the graph of parabola 13 minus x squared. It's just the parabola up and down, and the maximum value is 13. And we have a point P, and we have to find out the coordinates of the point P in the graph at which the tangent line passes through the point 7, 0. Okay, 7, 0. I can use, and we're looking for this point, y, x, xy actually. Okay, so what we can do, we have to find x and we have to find y. And this is a tangent line. This line is tangent, okay? Tangent line. We can use point slope form. Point slope form is y minus y1, and then slope x minus x1. And we actually know that that line goes through the point 7, 0, 7 and 0. Okay, excellent. That's okay, because that's tangent line. We're using this expression, which actually I can say mx plus 7, because of course. Oh, of course, wrong, because 7 is not a y-intercept. Did I mess up the 7 and 0? Value is 0. X is 7. Okay. Then we will have 7m. Okay, maybe even. Okay, but what we still need that magic number m. And what m is? M is a slope of the tangent line. Of tangent line, okay, tangent line at, and we don't know, at x. We actually don't know what is that x quantity. Okay, we know that the slope is defined as a derivative, right? This is derivative because slope of the tangent line is the derivative. The only thing is derivative at that x, not derivative at that 7. We may take the advantage of this point, which I took almost. Now it's correct. But we have to still use the derivative. Okay, let's actually find out. The derivative of the function 13 minus x squared is derivative of 13 is a 0 minus derivative of x squared is 2x. Okay, it means slope is defined as a negative 2x, but we still don't have that x. What we can do, we can also use just the formula for the slope, because slope of the tangent is just the slope of the line, and we do have 2 points. Let's actually say this: y2 minus y1, x2 minus x1. But let's figure out what. Oh, I just need a room. And I will assume that this is my x, and this one, like x1, y1, or x2, y2, that's okay. I can say y minus 0 because I'm using this one. And then x minus 7, because that's also the slope. That's also the slope. And what we can do now, we can try to combine them because they are the same. Oh, actually, one more step. Instead of y, we can actually, because that y, we can see x and y is on the graph, on the parabola, then this y satisfies the formula of the function 13 minus x squared. This is y. And minus 0, we don't have to, x minus 7. Excellent. What we can do, we can say that both of the formulas, this one represents the slope of the tangent line, and this one represents the slope of the tangent line. We can try to set up them equal to each other. 13 minus x squared over x minus 7 equals to negative 2x. Okay, negative 2x. Okay, and of course, x is not 7, we know that because for this equation, because that's different, this is just the other point. X is definitely different than 7, then I can cross multiply 13 minus x squared negative 2x times x minus 7, because I have to make sure that my equation, I'm not multiplying by 0. Let me add a slide, then we can, okay, that's what we have. We have 13 minus x squared, I can copy this, multiply by negative 2x times x minus 7. Let's distribute negative 2x squared, positive 14x. Now, let's add 2x squared to both sides. 2x squared and negative x squared will be 1x squared. Let's subtract 14x and add 13. Okay, we can try to factor out, and I believe 13 and 1, minus and minus, oh, x is missing. And now x equals to 13 or x equals to 1. We do have 2, but let's actually check something. Of course, we have to x equals to 1 because I'm just trying to find out the x13, we will not use that x13, right? Because that's outside, completely outside our domain. Okay, that means this is basically that value, x equals to 1. Let's okay, that means now let's, of course, 13, we will remove it because definitely x value is between 0 and 7. That will be the reason. And this is 1. And now we can compute y value, and y value, of course, satisfies again the formula of the parabola. And I can say this x and y will be value at 1. 13 minus x squared, 1 squared, 12. Okay, we have 112. 112 is the final answer. I can put on this graph 12. Okay, nice function, but of course, the sum of the application, just of the slope, and the slope from the new perspective. Slope of the tangent as a derivative. Okay, good question. Now, okay, I have another one. Find the points on the graph, and graph is the third degree polynomial 54x minus 2x cubed, where tangent line is horizontal. We don't really have to draw the graph because quadratic function, we will expect that we know the quadratic functions, but the polynomials, probably you know a little bit, but yeah, we don't have to, unless we really want. But let's first of all, let's set up the situation. We want all of the points where tangent line is horizontal. Okay. Condition for the horizontal tangent, of course, is derivative equals to 0. Okay, derivative equals to 0. This is the condition for the horizontal tangent line. Okay? If we will solve this equation, we can get all of the points where tangent is horizontal. Okay, let's try. Derivative of 54x is just 54. Derivative of 2x cubed is 6x squared. This has to be 0. Okay, we can try to factor out 6. I think this will be 9. And we will factor out. And now we can see x equals to 3 or x equals to -3. Both of them are in the domain of the function. Then yes, at these points, tangent is horizontal. But what we have to do, we have to find out what is the y value. Let's say this will be 0.1 and this will be 0.3. The second 0.1 and 0.2, 3 and -3, the x intercept. Let's substitute 3. We will have 54 times 3 minus 2 times 3 cubed. Big numbers. 54 times 3 will be 150, 162 minus 2 times, and this 3 times 3 times 3, I believe, is 27. 162 minus 54. Yeah, I always like my students to help me with the arithmetic. And we will have 6, 7, 8, 108. That means this is 108. And if we will substitute -3, this will be -27, right? Let me do it. Negative will give us positive. We will add this, and when we will add this, it will be 216. Okay, big numbers. Okay, and I think we will not, we made, but because of the numbers are too big, we can try to draw this graph, but I don't know if we can, just to have this, we have nice points. Actually, let's draw it. It's not a part, but let's just to have some idea. Can we manage to squeeze here? First of all, what we can do, we can try to find zeros, but I believe the zeros will be not a nice numbers, but 54, we can factor out x. Okay, let me just try. I'm just trying to, okay. Let's say this function is 54x minus 2x cubed. When we factor out x, we will have 54 minus 2x squared. Yeah, the problem is we can also factor out 2, but 54, 27, that's what I don't like. If this will be 25, will be a little bit better. But what we have 2x, and then square root of 27 minus x, and square root of 27 plus x. I'm just trying to find out the zeros. 2x is 0 if x is 0, and then one of the x is negative square root of 27 and positive square root of 27. And we of course know, because we can see the x cube, the leading coefficient of x cube is negative. If we will cube huge numbers, I'm just trying to find out the end behavior. If we will cube positive numbers, we will still have positive, but this minus will give us negative. Then we know that the graph is below for the positive. And then we simply have to, okay, and that's the polynomial. Also, we can figure out, actually, let me draw a little bit. Of course, you will see my scale is not good, because we know some of the values, but I just want to give you the idea. If we will cube the negative numbers, it will be negative. With this negative is positive. That's the reason that function is going this direction for the negative axis. And now let's look at this horizontal tangent, because that's the calculus part, and horizontal tangent. We know that is happening at -3 and +3. But of course, that number is 108. It's supposed to be way higher. And this one, oh, did I mess up something? Oh, okay. I think 108 is correct. I'm happy that I did the graph. I didn't put negative here. Oh, way bigger number. Let me put -3. Actually, let me put nicely. Yeah, you see, that's how we can make shortcut. -3 and -3 cube. -27, negative and negative is positive, but this will be actually minus. Okay, it's actually the same thing, but negative, because now instead of adding and subtracting, we're subtracting and adding. -108. Oh, okay. I'm so happy that I draw the graph. -108. Negative, let's be consistent, -108. Okay, either way, my graph's supposed to be a little bit higher, but now we do have a nice graph and points for the horizontal tangent. Nobody will question that definitely at these points we have horizontal tangent. Okay, And we can see how nicely we can get these points, 108, 108, negative, of course. Okay, and I have one more question. And we will be an experts with the graphs of the derivatives and horizontal tangent and horizontal tangents. Okay, find the graph of the derivative for the function below. And the function looks like this. Yeah, let's try to draw it. We have some tools, of course, slope of the tangent. Okay, we will start with this. Horizontal derivative is 0, then we will have x-intercept. Derivative is 0 because horizontal, we will have x-intercept. And derivative is 0 here. Slope is 0, of course. Then we have zeros. And now let's just see if function is increasing, right? All of the slopes are positive. Then the graph of the derivative has to be above the x-axis, right? Nice hint. And now these are almost horizontal, small numbers. And then it's a little bit bigger. And at some point, probably here, it's kind of like a maximum. Let's say here, I don't know, maximum. And then it's again getting steeper. It's less steeper because it's approaching horizontal. Okay, I would say small numbers, kind of like maximum, and this. Now, quite steep. Now, between that point and this one, first of all, function is decreasing. Slope is negative. Quite steep, right? And it's, again, kind of like steeper here with the negative values that we will, yeah. And then it's again getting less steeper and approaching 0. And the same thing, it's getting steeper and steeper and steeper. At some point is the steepest, maybe here, yeah, the values, and then it's getting smaller and smaller and approaching 0, approaching horizontal. And then this, it's extremely steep in the negative values. Okay, if this is f of x, this is a beautiful graph of the derivative. Thank you.